Hi all, welcome to another session of Boilchem Tutor. In this session, I am discussing mainly about 5-membered heterocycle, that is thiophene. In that, I am mainly discussing what is thiophene, where it is occurred, what are the method of preparations of thiophene, what are the physical properties, and lastly, I am discussing about their chemical reactivity. Coming to the first topic, that is what is thiophene. Thiophene is a 5-membered heterocycle obtained by the replacement of a carbon-carbon double bond of a benzene by a heteroatom, that is sulfur. Moreover, the sulfur contains an unshared pair of an electron which help in the delocalizations of the pi electrons present in the ring, thereby making the thiophene as an aromatic compound just like that of a benzene. Its IUPAC name is thiol. And coming to the positions of thiophene, is second and fifth positions are termed as the alpha position, and third and fourth position are termed as the beta position in thiophene. So coming to the next topic, that is where thiophene is occurred. Thiophene mainly occur in coal tar. So during the fractional distillations of the coal tar, we will get thiophene along with benzene, because thiophene and benzene is having a comparable boiling point. That is, thiophene is having the boiling point of 84 degrees Celsius and benzene boiling point is around 80 degrees Celsius. So benzene always contains 0.5% of thiophene. Therefore, it should be carefully treated to obtain a thiophene-free benzene by the fractional distillations of coal tar. So, in order to separate thiophene from benzene, the mixture is usually treated with cold sulfuric acid, so that thiophene will easily react with the cold sulfuric acid to form thiophene sulfonic acid, and which is readily soluble in water. So after getting thiophene sulfonic acid, it is treated with superheated steam to recover thiophene from benzene. Another better method to recover thiophene from benzene is by refluxing with aqueous mercuric acetate, so that thiophene will get easily mercurated but benzene remain unaffected. After getting the mercuric derivative of thiophene, which is carefully distilled with hydrochloric acid to recover thiophene. Coming to the next topic, that is how to synthesize thiophene. There are several methods to synthesize thiophene in the laboratory as well as in the commercial scale. Here I am discussing some of the important methods to synthesize thiophene. That is one from furan, next from furoic acid, next from butane, then acetylene, then from sodium salt of succinic acid, and lastly by Paulnor synthesis. And this Paulnor synthesis is specially designed for synthesizing a substituted thiophene. Coming to the first method of synthesis of thiophene, that is from furan. So when furan is treated with hydrogen sulfide, the oxygen atom present in the furan ring is easily replaced by sulfur, thereby we are getting thiophene with the eliminations of a water molecule. Coming to the next method of synthesis, that is from furoic acid. Furoic acid is actually a furan with a substitution, that is carboxylic acid. So when this furoic acid is treated with barium sulfide, the oxygen atom present in the furan ring is replaced by sulfur. Moreover, this carboxylic acid group gets decarboxylated and which will be eliminated as barium carbonate. Coming to the next method of synthesis of thiophene, that is from butane. When butane is treated with sulfur, we are getting thiophene, and the hydrogen atom from the butane are eliminated as hydrogen sulfide. Coming to the next method of synthesis of thiophene, that is from acetylene. So when acetylene is mixed with hydrogen sulfide and it is passed through a red hot tube, and with alumina as a catalyst, that is Al2O3 as a catalyst at high temperature of around 673 Kelvin, we are getting thiophene as the product. So coming to the next method of synthesis of thiophene, that is from sodium salt of succinic acid. When sodium salt of succinic acid is treated with phosphorus trisulfide, we are getting thiophene, and it is one of the easy laboratory method to synthesize thiophene. Next, we can discuss the synthesis of a substituted thiophene by Paulnor synthesis. In Paulnor synthesis, we are taking 1,4-dicarbonyl compound and which is treated with peroxydisulfuric acid, that is H2S2O8. Then we are getting a substituted thiophene in the laboratory. So let us discuss the mechanism of getting substituted thiophene by Paulnor synthesis. The first step in the mechanism of Palnor synthesis is the attack of a proton, that is attack of an acid to 1,4-dicarbonyl compound. And this carbonyl oxygen is having a lone pair of electron, and so that the lone pair electron present in the oxygen atom get attracted the proton and thereby it get protonated. So next step in this synthesis is the attack of a sulfur, and this sulfur is obtained from S2O8, and sulfur is having a lone pair of electron, and so it start donating and to this protonated species, and there form a bond between sulfur and the carbon, so that the sulfur become negative charge. And next step in the mechanism is the eliminations of a water molecule and resulting in the formation of a double bond between the carbon. The next step in the synthesis is again the attack of the acid to the next carbonyl oxygen, and this oxygen is having again lone pair of electron and it start attracting this proton and get protonated. Then the next step in the synthesis is the sulfur is having a negative charge and which get donated to this carbon and thereby forming a bond between the carbon and sulfur, so that a ring is formed. Then the last step in the mechanism of the Palnor synthesis is the eliminations of a water molecule and resulting a carbon-carbon double bond and resulting in the formation of a substituted thiophene by Palnor synthesis. So coming to the next topic, that is physical properties of thiophene. It is a colorless liquid. It is insoluble in water, but it is soluble in organic solvents such as alcohol, ether, chloroform, etc. It has a benzene-like odor and moreover its boiling point is around 357 Kelvin. So coming to the resonating structure of thiophene, in thiophene, sulfur is having a lone pair of an electron, so it start donating to the ring and thereby sulfur become positive charge and negative charge will occur at the third position in the first resonating structure, and then the negative charge will start to shift at the entire position of the carbon, and so that we can conveniently represent the resonance hybrid as the last structure, that is with a ring inside the 5-membered ring. Again, when we compare the aromaticity of thiophene with other 5-membered heterocycles such as furan and pyrrole, thiophene is found to be more aromatic than that of the furan as well as the pyrrole. But it is less aromatic than that of the benzene. And this can be easily explained with the help of a resonance stabilization energy data. The resonance energy of furan is found to be very less, that is 17 kilocalorie per mole, and whereas thiophene is found to be 29 and pyrrole is found to be 21 kilocalorie, and we already know that more resonating energy means more and more stable and it becomes less reactive. So thiophene is having high resonance energy, therefore it becomes more aromatic when compared to the furan and pyrrole. The high aromatic character of thiophene can also be explained with the help of an electronegativity scale, and when we compare the furan, pyrrole and thiophene, the furan oxygen is more electronegative when compared to the thiophene sulfur. And so when electronegativity scale or electronegativity of sulfur decreasing means it can easily donate that electron to the ring. Thereby it will help in the delocalizations of the pi electron easily. So the thiophene become more aromatic when compared to the furan as well as the pyrrole. So the aromatic order of these 5-membered heterocycle will be furan will be least aromatic, then comes the pyrrole, then comes the thiophene, then comes the benzene. That is, thiophene become more aromatic than that of the pyrrole and then that of the furan, and but when we compare the benzene and thiophene, benzene become more aromatic because it is having the resonance stabilization energy of 36 kilocalorie, which is higher than that of the thiophene. But when we discuss the reactivity of the thiophene with the other heterocycle, it is found that pyrrole is more reactive, and then comes the furan, and then comes the thiophene, and then comes the benzene. This can be explained as follows. Actually, the reactivity of these heterocycle on electrophile depend upon three major factors. One is it mainly depend upon the availability of the electron on the carbon atom. Next, it depends upon the electron release from the heteroatom. That is, if the release of electron from the heteroatom is easy, means it will be more reactive. Next, third factor will be the greater stabilizations of the transition state. That is, when electrophile is attached, if a greater stability of the resonating structure are obtained means it will be more reactive. So when we look this heterocycle, that is pyrrole, furan and thiophene, we found that the pyrrole nitrogen atom is trivalent. That means nitrogen is surrounded by 2 carbon atom and 1 hydrogen atom. So the inductive effect is more. That means this will make the nitrogen electron rich. And so that the release of electron from the nitrogen also become easy when compared to furan as well as the thiophene. And so that electron availability on the carbon atom also will increases, because electron release from the nitrogen atom is increasing means the electron availability on the carbon atom also will increases, and there will be greater stabilizations on the transition state also will be occurred. So pyrrole become more reactive than that of the furan. But when we compare the furan oxygen is more electronegative. So it will pull the electron towards the oxygen itself. So electron release by the hetero atom become less. So that electron availability on the carbon atom also become less. So that the stabilizations of the transition state also become less. That is why furan become less reactive when compared to the pyrrole. But when we look at thiophene sulfur is having least electronegativity. So the release of electron by this heteroatom, that is sulfur, will be easy. So that it help in the delocalizations of the pi electron. That means aromaticity is increasing. If aromaticity increases means reactivity will be less. But the availability of the electron on the carbon atom is less due to the fact that the mesomeric effect, that is resonating effect, is smaller. And due to the fact that the carbon and sulfur, there will be size difference will be there, so that there is a non-effective overlapping of the p orbital. That is why its reactivity towards the electrophile decreases in thiophene. So when we look at the reactivity order, pyrrole is more reactive, then comes the furan, then comes the thiophene, then only comes to the benzene. So that is all in this session. Hope you like this session. Stay tuned for the next session. Till then, bye.